is Science Fantastic with Professor Michio Kaku. On Science Fantastic every week, we profile some of the most amazing developments in science and technology. And today, we're going to talk about something so familiar that we barely notice it, but it's so important for the space program, so important for our very lives, and that is the sun. That's right, something that we often forget. With us today is Colin Stewart, science journalist all the way from England, author of a new book called Rebel Star, Our Quest to Solve the Great Mysteries of the Sun. Well, recently there's been a number of successful launches indicating that we're entering a new era in the exploration of outer space. You know, for decades, NASA was criticized for being the, quote, agency to nowhere. Yes, it went to the planets, but not much other than that. Humans are no longer exploring outer space. Well, that's changed. Because of billionaires now dumping money into this game, because of renewed spirit of exploration in NASA, we're seeing a new age in the exploration of outer space. In fact, I think we're going to have a traffic jam around the moon in the coming years. By 2024, for example, the first men and women will go back to the moon after so many decades of not exploring the world. But hey, let's be honest about this. There are problems. One of the biggest problems is solar flares and radiation. You know, to go to the moon, it's a hop, skip, and a jump. 3 days, and you're on the moon. That's all it takes to go to our nearest celestial neighbor. But to go to Mars, that's the new destination. To go to Mars takes 2 years for a round-trip mission. 9 months to get there. A few months to do research and to wait for the next cycle, and then another 9 months to come back. And we have to worry about radiation. We have to worry about solar flares. So we have to worry about our sun, something that we take for granted. But did you know that a solar flare could literally wipe out communications on the planet Earth? It happened. In the mid-1800s, the Carrington event, a gigantic solar flare that wiped out telegraph communication on the planet Earth, because back then that's all we had. Could we have another Carrington event again that could wipe out telecommunications, GPS, the Internet, all of that on the planet Earth? Well, with us today is Colin Stewart, science journalist, author of a number of great books, including 13 Journeys Through Space and Time, Christmas Lectures from the Royal Institution, and The Universe in Bite-Sized Chunks. So once again, our special guest today is Colin Stewart, who will walk us through Rebel Star, our quest to solve the great mysteries of the sun. So, Colin, let me ask you a personal question. When you were a youth, when you were a kid, what steered you in the direction of science and eventually astronomy?
Well, thank you for having me. I think it was really to do with the fact that I realized that the space was real. And let me explain what I mean by that. When we're kids, we get told these, all the time we're being told stories of witches and goblins and giants. And I realized that the stories that I was being told about space, whether that's Jupiter or black holes or the sun, they were real. They weren't made up. And to me, they were every bit as enthralling and as fascinating as those made-up stories, and that had me hooked from that point onwards.
Okay, well, let's just jump right into the contents of your book, Rebel Star, Our Quest to Solve the Great Mysteries of the Sun. Well, when I was a kid, we were told that our sun is kind of ordinary. It's an average yellow star, not much different from the other stars in the Milky Way galaxy. But you titled your book Rebel Star. So the first question for you is, why that title?
So it's not that the sun is a rebel compared to the majority of other stars. I mean, that idea of it being average is slightly wrong, because the vast majority of stars in the universe are considerably smaller than the sun. So there are only about 15% or so of stars that are bigger than the sun. So it's not average, really. But the rebel part of it was that it's been very stubborn with giving up its secrets over the centuries. It's been a very hard thing for us to get to the bottom of, the way that it works and to understand it. So in that sense, it's a rebel that it seems to have kept its cards close to its chest and doesn't like to reveal its secrets too quickly.
Okay, well, let's just get some of the basic questions out of the way. First of all, how hot is the sun? And of course, no one's ever been there. It's too hot. So how do we know that that is the correct temperature of the sun?
Yeah, so it depends what way you're talking about on the sun. The surface, the visible surface that we see, called the photosphere, that's 6,000 degrees Celsius. But the deeper you go inside the sun, the closer and closer you get to the middle, the more the temperature rises. Until by the time you get to the very center of the core, we're talking about a temperature of 15.7 million degrees Celsius. And we know that because we have an amazing thermometer. Like you say, we can't go there. We can't stick a physical thermometer in the sun. But we're pretty confident we know where the sun's energy is coming from, the nuclear processes that make sunlight. And they produce these reactions, not just sunlight, but these tiny invisible particles called neutrinos. And they are so sensitive to temperature that the number of them that get produced are so sensitive to temperature that makes them an excellent thermometer. You know, change the temperature just a little bit and you drastically change the number of neutrinos being produced. So from that, we can very accurately say that down in the center it's 15.7 million degrees.
Okay, and then what is the energy source? Because since time immemorial, scientists have speculated that if the sun were made out of oil or gasoline, it would have extinguished itself billions of years ago. So what is the energy source of the sun?
Yeah, I mean, that idea goes back to Lord Kelvin, and the same guy gives us the Kelvin scale. He was thinking the sun was powered by, like you say, the gravitational contraction. Instead, it's something called fusion, nuclear fusion, which is simply turning hydrogen, the lightest element in the universe, into helium, the second lightest element. And in the process, that liberates energy. So every second, the sun is turning 620 million tons of hydrogen into 616 million tons of helium. So there are 4 million tons missing. 620 million in, 616 million out. And it's that missing 4 million tons that's turned into sunshine. So every second the sun is generating 4 million tons worth of sunshine. Okay,
well, let's hope that the sun doesn't erupt, because if the sun has a temper tantrum, we're in big trouble. Welcome back to Science Fantastic with Professor Michio Kaku. Once again, our special guest today is Colin Stewart, science journalist, author of a new book called Rebel Star, Our Quest to Solve the Great Mysteries of the Sun. And one of the greatest mysteries of the sun is the fact that once in a while it has a temper tantrum, throws off a huge coronal mass discharge, and if one of these discharges hits the Earth, we're in big trouble. And something like that actually happened. This is not science fiction. Back in 1859, the Carrington event was observed when the sun basically almost ejected a tremendous amount of explosive energy, which hit the Earth, wiping out telegraph wires. So tell us a little bit about what happens when the sun goes crazy.
So it's to do with the sun's magnetic energy. So you can imagine it a bit like a rubber band, an elastic band. If you constantly twist it up, you're storing energy inside. And it can only take so much. Eventually, it's going to snap. And it's the same with the sun. It stores up magnetic energy, and eventually it becomes too much, and it bursts out of the sun. Now, we're talking about more than the mass of Mount Everest. 1 billion tons of material released at 1 million miles an hour. So these coronal mass ejections, these CMEs, are huge. Now, the sun does this all the time. I mean, when the sun's at its busiest, a period we call solar maximum, it's doing this 2 or 3 times a day. Now, fortunately, we live quite a way downstream of the sun. And so for these eruptions to be pointed straight at us is a pretty rare event. Now, like you say, the biggest one we have on record, the Carrington event from 1859, observed by Richard Carrington, a fellow Englishman. He actually was working about half an hour drive from where I am right now. And it was the first time we realized the sun could be this explosive. And the bad news is these events, we reckon statistically, they'll be big enough and hit the Earth every 150 years or so. And we're looking at 1859 for the last big one. If you wind 150 years forward, you get to basically now. So we're overdue one of these huge explosions. I'm afraid it's another corona thing, another thing with corona in it to add to the list of things we need to worry about.
Now, back in 1859, all we had electronically were telegraph wires, and some of them caught on fire, according to the data that was accumulated back then. Today, we have satellites. Today, we have the Internet, GPS. We have much of our economy done in outer space. Plus, we have the space station. We have astronauts living in outer space. So give us a little clue as to what might happen if we have a direct hit from another Carrington event. What might happen?
So we're talking about something much more serious in 1859, partly for the things you mentioned, our space infrastructure. So the extra electricity that comes with the storm would fry the circuits of the satellites on that side of the Earth. So knocking out most of our GPS satellites, for example, as you say. For us on the ground, there's an even bigger problem because there'll be so much extra electricity flowing through the atmosphere that it will pass through our power grids, the normal power lines that carry our electricity. And they're only designed to deal with so much current, and if they get more than they're allowed, they'll burst. What will happen is that the transformers, they're the machines that carry the electricity from place to place around. The oil inside will boil and they will break. Now, if you've ever seen an electrical transformer, we're not talking about a tabletop device. We're talking about something the size of a house. We don't have a lot of spares. These things are huge and expensive and difficult to build. So it could take months and months to get the lights back on, to have enough transformers to get back to the way we were. So, we would be looking at power cuts lasting months at a time. And if you think about the consequences of that, that's annoying for us, right? You can't plug your phone into the wall. Maybe your internet doesn't work. But it's a lot more serious when you think, well, hospitals need power. Now, okay, they have backup generators that can allow them to do the most serious operations. So if your life is in danger, you're probably all right. But let's say you break your leg, or you cut yourself, or you burn yourself, something not life-threatening, but pretty serious. You're going to have to wait because the queue for treatment is going to be so much higher than before because they really have to ration their electricity. Gas stations, the inability to get cash out of an ATM, all of these things that we rely on will suddenly go away. So in a way, it's the reverse of what we're experiencing now with coronavirus, right? We can't really see each other very often. We can't be in the same room as each other. But thankfully, we have power. We have internet. We can do video calls. It's been revolutionary to have this. Imagine if it happened 15 years ago without video calls. A corona mass ejection is the opposite. You can see who you want, but you have no power, no phones, no internet, no video calls, no teleworking, working from home, all that sort of stuff. So it's a different challenge, but it's one that's just as serious.
Now, a group of physicists did a study showing that property damage to the world economy with another Carrington event would be on the order of $2 trillion. That's trillion with a T, not a B, $2 trillion US. That's a lot of money. The reaction of the Congress was, the so-called giggle factor. A lot of Congress people simply giggled, laughed, and dismiss the whole thing as science fiction. But let's say we are to really do something. What could we do? Could we reinforce and have redundancy in our power stations, reinforce our satellites? What could be done to protect us from another Carrington event, which we know is inevitable?
So as with most things in life, knowledge is power. Now, unfortunately, we can't do anything to stop these events from happening. Now, that's engineering on a scale way beyond our means. But if we know it's coming, then we can take evasive action, right? So if you know a hurricane is coming, you take action. You maybe evacuate. You board up the walls, board up the windows. You can only do that if you've got a decent weather forecast that tells you the storm is on its way. But it's the same with the sun. We need notice, because the key thing is which way the storm is pointing is key. Our magnetic field, the Earth's magnetic field, runs from the South Pole to the North Pole. So it's going up from Antarctica to the Arctic. If the magnetic field of the storm points the other way, so it's pointing south, that's the really dangerous storms. If it's pointing the other way, the same way as our magnetic field, it's not a problem. We don't get the same damage. So the crucial thing is knowing which way the storm is pointing. And right now we don't know that until at most 12 hours before. Sometimes it's a lot less than that. So the key thing is predicting the storm, having a space weather forecast, in the same way we have a terrestrial weather forecast. And we have come a long way with that in recent years. I mean, here in the UK and the US are the only places to have a civilian space weather forecast service. And so we are getting there, but we're still nowhere close to being where we need to be for something as big as the Carrington event.
Now, you mentioned that they happen roughly every 150 years, but how do we know that? I understand that ice cores, by digging into the ice of the North and South Pole, you can actually pick up the time when the Carrington event took place, and it's etched in the ice. However, that's a very crude process. So how do you know that another event could take place within a span of 150 years, which means we are overdue?
So it's a statistical idea. So I guess it's the same as, you can say that there's a 1 in 100 year a storm reaching you. So it is an estimate. And there's a bit of wiggle room there, right? So it's not like you're definitely going to get one every 150 years. It's if you average it out over, tens of thousands of years, you would expect to get one roughly at 150 year intervals.
Back to Science Fantastic with Professor Michio Kaku. Once again, our special guest today is Colin Stewart, all the way from England. The book is called Rebel Star, Our Quest to Solve the Great Mysteries of the Sun. And because of the fact that we're putting our astronauts in outer space once again on U.S. rockets, it means we're entering a new era in the space program. But one of the dangers, once you leave the Earth's protective atmosphere, one of the dangers is cosmic rays, radiation from the sun, solar flares. A whole list of problems starts to develop. And so, Colin, let me ask you a question about outer space. How dangerous is it for our astronauts when they leave the Earth, go through the Van Allen belt, go into deep space? How radioactive is outer space? What are the dangers of going all the way to Mars on a mission that'll take maybe 2 years?
So that is probably the biggest issue we have to get over if we're going to make human missions to Mars a success, because we've evolved on the Earth under a lovely protective blanket of atmosphere and magnetic field that shelters us from this stuff the sun kicks out. And it's not just the sun either. It's the wider universe. Supernovas and other cataclysmic events throw out radiation. So the radiation environment in space is really a real problem. I mean, the Apollo astronauts, they were just lucky. You mentioned earlier it's a 3-day trip. But in 1972, there was a coronal mass ejection that hit the Earth. Now, it wasn't as big as the Carrington event, but it was still pretty big. And it happened right between two Apollo missions. Now, if the Apollo astronauts had been on the surface of the moon at the time, it would have been touch and go whether they made it. They would have had to come back to the Earth immediately for a bone marrow transplant in order to give them any chance of survival. Now, a 10-day hop to the moon and back, you can get lucky. A 2-year trip to Mars and back, you're just not going to dodge that threat. And so we need a way. Again, you can't really. You have to protect the astronauts from that radiation somehow, but we don't have a lightweight way of doing that. I mean, if you think about a hospital, if you have an X-ray, the radiographer will stand behind a LED screen to protect them, but you can't make a LED screen for a spaceship. It's far too heavy. So that's the issue. We have to come up with a way of keeping astronauts safe, because then if we don't, we're looking at things like cataracts, radiation sickness, cancer. It'll kill you if the dose is high enough.
And let me ask you a question about the solar cycle, which allows us to give us some predictive power. Every 11 years, we have the sunspot cycle. And there's a theory that says that these sunspots can act like rifles that shoot out coronal mass discharges. And we're the duck. We're the sitting duck out there in outer space, waiting for us to be hit by one of these coronal mass ejections. But tell us, what is a sunspot and what are the solar cycles?
So a sunspot is as it sounds, really. It's a dark blemish on the surface of the sun, a bit like a spot on a teenager's face, but it's black. And all it is a cooler region of the sun. And the reason it's cooler there, about 1,000 degrees cooler than the surrounding area, is because of magnetism. Where there is really intense local magnetism on the sun, it stops as much heat rising up from below as elsewhere. So we just see a cooler spot. But we do know, and we've known since the 1800s, that the number of sunspots we see seems to, as you say, cycle, rise and fall in a regular way.
Welcome back to Science Fantastic with Professor Michio Kaku. Today we're talking about, some of the dangers that our astronauts will face as they are launched back to the moon and even beyond that on to Mars, far beyond the Van Allen radiation belt, into deep space where they have to worry about cosmic rays, coronal mass ejections, solar flares, all the dangers of outer space. So the book is called Rebel Star, Our Quest to Solve the Great Mysteries of the Sun by Colin Stewart, who we have with us right now all the way from England. Well, when we last left off, we were talking about sunspots. Now, if you want to see a sunspot, of course, you got to be careful. Get a sheet of paper, put a pinhole in that sheet of paper, shine it in the direction of the sun, and you can see the image cast by the sun, and if you're very good, you can see tiny little sunspots on the surface of the sun. According to legend, Galileo himself accidentally looked at the sun directly and burnt a piece of his retina. Of course, that is a tale that we tell our students to be careful if you look at the sun with a telescope. But with us today is Colin Stewart, who'll talk to us about some of the dangers our astronauts face. So why do we have this 11-year cycle? And is there a peak of solar activity during this 11-year cycle that we have to worry about?
So, it's on average, it's 11 years. So sometimes it's been as short as 9 and sometimes as long as 14, but it averages out over the centuries at 11 years. The trouble is no two cycles are equal. Sometimes we get a really busy cycle, sometimes we get a really shallow cycle. The simplest way to think about why it cycles in this way is that it takes time to wind up the sun's magnetic field. It's a bit like the rubber band, elastic band that I was mentioning earlier. It takes time to wind it all up. It snaps, and when it bursts out of the sun, we see lots of sunspots, lots of flares, lots of coronal mass ejection. And then things quieten down for a time, as it takes more time to wind everything back up again to reach the peak. So that's why we get this yo-yoing of up and down and up and down. And at the peak, we do get one or two sometimes 3 coronal mass ejections a day. The flares, these are these sort of small bombs going off on the sun. The peak of the flare cycle is slightly offset from the normal sunspot cycle by a year and a half or so. So you don't necessarily get the most flares at solar maximum, but it's closely linked. So what you don't want to do basically is go to Mars at solar maximum. You'd rather go to Mars at solar minimum, because then that reduces your chances of you being hit by solar material.
So there is a certain amount of predictive power, right? I mean, you can time your space shots to avoid when the sun is at its peak, right?
Yes, exactly. We can say that with some certainty where maximum is going to be, and even if you give yourself a couple of years leeway, you're likely to be somewhere where the sun's quieter. So right now, for example, I mean, I think you'd be quite lucky to see a sunspot through a pinhole camera at the moment, because the sun is so quiet. We're at solar minimum, that sort of trough. So now would be a good time to go to Mars. Unfortunately, we don't quite have the rockets yet, but 11 years from now, 22 years from now, 33 years from now, you're also going to be at a similar stage in the cycle, so that they would be very good times to go.
Okay, now let's talk about the fact that there are mysteries that we still don't understand about the sun. You mentioned the temperature on the surface of the sun being roughly 6,000 degrees centigrade or so. But if you go further away from the sun and go to the corona, then it's much hotter. Now, it should be the opposite. How is it that the further away you go from this hot furnace, the hotter it gets, which violates common sense?
Yeah, it definitely violates common sense. I mean, if you think about it like a campfire, imagine you started walking away from a campfire, and then you started to get a bit cooler, as you'd expect. And then you keep walking further from the campfire, and suddenly things get hotter again. Right? We know that's not how heat works. So there must be something else at play. There must be some process, or maybe a mixture of processes, at the surface of the sun, injecting energy much higher up into the very outer layer of the sun's atmosphere. We have some guesses as to what that could be. So one is something called nanoflares.
Okay, let's take another short commercial break. Welcome back to Science Fantastic with Professor Michio Kaku. Today we're going to do something that most of you rarely do, and that is look up. You know, we spend most of our time looking down, thinking about all the problems we have, all the things we have to do, all the to-do list of things that it's got to be taken care of. We look down for the most part. But why don't you look up to the stars and to the sun briefly, and you realize there's a whole universe out there. Well, the universe has many mysteries, and one of them is the temperature of the sun. The sun, by right, should get cooler the farther you get away from the solar furnace, but that's actually not true. So what do we know about the fact that the temperature of the corona of the sun, which surrounds the sun, is actually hotter than the surface of the sun? How's that?
It's considerably hotter too. Just to put it into context, the surface is 6,000 degrees, as we've said. But the corona, this outer layer, is 1 or 2 million degrees. So there must be something at the surface of the sun that is injecting energy up into the corona. And to be honest, we don't know what that is, although we have some educated guesses. One is something called nanoflares, which is exactly the same as a solar flare, talked about, but much smaller. So the same process, just on a much smaller scale. So small that right now we can't see them. They're too small to see. But if enough of them are going off together on the sun, these little detonations everywhere, then that could be doing it. Another thing that's a possibility is called an Alvan wave. And the best way to picture this is as a wave on an ocean, right? So a wave on the ocean carries a surfer to the beach and dumps them on the shore. Well, what an Alvan wave would do would be carry material out from the sun and dump that energy, further out into the corona. It could be both of those things. It could be neither of those things. It could be one of those things, or it could be something else entirely. So that's why it's the coronal heating mystery. We haven't solved it yet.
And let me ask you another question. The poets asked the question, will the world end in fire or ice? Well, we know the answer. The Earth is going to end in fire when the sun uses up its hydrogen fuel, expands into a red giant, and eats up the Earth. And Bertrand Russell, the great British philosopher and mathematician, wrote perhaps one of the most depressing passages in the entire English language, saying that for all the tears we shed, it's all for naught. It's all useless. All the trials and tribulations of humanity, totally useless, because it's all going to end when the sun destroys the Earth. Well, today we have the space program. Bertrand Russell didn't understand that, yes, one day we will leave the Earth. So tell us a little bit about what happens when we have the last nice day, the sun expands, so the sky's on fire, the mountains will melt, the oceans will boil, and we will go back into the sun. Explain how everything's going to end, unless, of course, we have a space program.
Well, the bad news is it's worse than that. So the sun will start to expand and engulf Mercury and Venus and possibly the Earth in about 5 billion years. But in just 1 billion years, the sun will be too hot for water on the Earth. Because the sun, as it gets older, gets brighter and hotter. Something called main sequence brightening. So in just 1 billion years, it'll be where it is, but so hot that water on Earth will have boiled away long before the sun starts to expand. But then you're right, the sun expands and will make the situation worse. So we don't have 5 billion years, we only have 1 billion years. Still, that's a long time. So you could say use space travel, you go to Mars maybe, which is further out. By then it would be warmer because the sun's warming up. You could go further out, maybe the icy moons of Jupiter, such as Europa, or the icy moon of Saturn, Enceladus. It might not be so icy, it might be more watery if things warm up. But that's a temporary reprieve, I'm afraid, because the sun is still going to be extinguished eventually. It will puff its outer layers into space and become a small Earth-sized blob. So it's a temporary reprieve. If you still want to stay, you still want to persist, you're going to have to leave the solar system and find somewhere else to go.
Well, the dinosaurs did not have a space program, and that's why they're not here anymore. We could also go the way of the dinosaurs when the sun eventually dies, taking us with it, unless we have a space program. But one thing that's not going to happen is that we're not going to have a black hole where the sun is. Now, there's a star called Betelgeuse in the constellation Orion. It's unstable. Astronomers are looking at it very carefully, an unstable star, and Betelgeuse could go supernova. So tell us a little bit about supernova. Our sun will not undergo that process, but tell us a little bit about what happens when Betelgeuse undergoes supernova and lights up the night sky.
So if Betelgeuse weren't to do that, and to be fair, it's going to do it at some point, and we always say soon, but you have to remember that's astronomically soon. So that's, within the next few million years, it would be brighter than the full moon. So you'd see it during the day as well. So we're talking something fearingly bright. Like you said, for the sun, it's not going to do that. It's not heavy enough. You have to be 8 times the mass of the sun or heavier in order to go supernova. It basically boils down to the core. If the core of the star is really heavy, then at the end of its life, it will collapse in on itself. And when it collapses, it rebounds, and that rebounding sends a shock wave out through the outer layers of the star and blasts it apart. And you have your supernova, which is as bright as a galaxy for a time. A galaxy containing 100 billion stars is matched in brightness by a single exploding star for a time as it then begins to fade away.
Okay, well, unfortunately, our time is up. So once again, our special guest has been Colin Stewart. Thank you so much for being on Science Fantastic.
Thanks for having me.
And once again, if you want to check it out, then check out his book. The book is called Rebel Star, Our Quest to Solve the Great Mysteries of the Sun.